you guys, can we do a sound check? Folks in the back? Okay, great, thank you. So I named my firm a design firm because it's very purposeful here. I wanted to emphasize design as a creative activity, and so starting over and starting a new firm, you know, I get to reinvent myself. It's like being a freshman when you pick your major. So it's like, damn it, I'm going to be a designer. So that's how we're starting. And the theme is finding the space between the rocks. And what I'm talking about with rocks is these are obstacles. And there are like thousands of ways projects can run into obstacles and fail. And I was thinking about, any of you guys mountain bike, you know, where you're going down a trail and all the obstacles are coming at you. And if you think about not hitting something, your body gravitates towards the obstacle. And what you have to do is you have to think about the space in between, which is like the solution. And I find that a really helpful image for me because like that's what we're looking for. And so especially in this sort of dynamic tension between engineers and architects, like I know, again, hundreds of ways why things can't work. And I don't need to prove why they can't work. What I need to do is help find how they can work. So let's take a step back and just talk a little bit about design process for a second. Now this is right up here, these are the design processes from the lean IPD world. But you can think of them as conceptual design, design development, schematics, and all of that stuff. But this is sort of the lean version. And in a traditional design, you see a separation of the owner, the architect, the engineers, and the builders. And you notice that we're separated by space and time, and it's the natural creation of silos here. And there's a real big one between the owner and the architect, and then another big hard handoff and the place where things break down between architects, engineers, the design team, and the builders. Now, in the lean or IPD ideal world, there's this form right here where we think, and it's in some ways it's more aspirational than real yet. But the idea is that we're all in it together, and that there's the assembly of a team, and the activities of the team change over time. And so in the beginning, we're thinking about programming, the business case, the owner's values, the big ideas. In the end, we're thinking about execution, speed, quality, making it happen. Now, what that sort of implies here is that builders and engineers need to think about, you know, we need to be designers and think like owners in the beginning, and then everybody needs to think like a builder at the end. And so it's calling on us to have a broader perspective of our roles. We still have our specialization. Have you folks heard of like T-shaped people? Anybody heard that? Okay, Randy has, of course. Okay, so a T-shaped person, the vertical axis represents your deep specialization. You know, like you got to be really, really good at whatever you're doing. So like if you're a mechanical engineer, you need to be really good at computational fluid dynamics. But you also need a broad perspective to know content and fit and how all these things interplay. So I think collaborators need to have these qualities, both depth and breadth. And so this is the ideal, how we move through time. And what I want to explore is like how we learn how to work together. I'm more interested in the process of work than the actual work itself. Or I'm interested in both, but really interested in the process. So thinking about, like in a traditional design, we think of like an iterative spiral. And in real practice, one of the things I've always found is we have time to only get through that spiral once. There is no time to get through to cycle through and truly iterate. And so that spiral actually sets up the relationships between all the parties and the handoffs and starts encoding various elements of how that design will come out. And in the end, we find the total cost and we find it's too expensive. And this happens like 80% of the time. And when it's too expensive, value engineering is really a slash and burn rating of finishes. Like the thing that goes is the landscape budget and then the finishes. Because the deep systems, like the structure and the mechanical forms and all that stuff, there's not enough time to go around again and figure out how to do it, how to economize. So I'm proposing, and a lot of people have been proposing this idea of set-based design. And in set-based design, there is a recognition of exploration of multiple branches, but it's done from a coarse level to a fine level. And so we're sort of moving through time. And as you explore, this diagram draws this wavy line. The reason it's wavy is that's the design team wandering around because we don't really know where we're going. We have a feeling, you know, we're exploring. This is a diagram of an exploration. And we think, after some amount of work, and this is time and money, that there is a presumed outcome. And so we're exploring, say, 3 options, and we think this outcome's there, and we decide to choose this outcome when we have confidence that that's where we're going. So the point is the exploration until you have confidence. You can't explore till you know exactly, because then you've spent too much time and money. Then, from this point, you explore finer portions of the design until you have confidence, and then you leap again, and finer and finer and finer. So it's a progression through the design process that incorporates exploration, quick modeling, and it explicitly acknowledges risk. And so in my world, in the structural world, I'm not trying to get precision or accuracy. I'm trying to get a feel of what's going on so I can convey information so the team can make decisions. You need to know enough to make a decision. And in that needing to know enough, the speed of an exploration matters more than the accuracy. Because you need to, again, you need to be able to figure out, how do I get here? And then how do I get there? And how do we progress through there? So that's a concept I'd like you guys to leave you folks with. And this image is from one of my favorite architects out in Kansas City, BNIM. And this is just a display of all the systems in a building project. And the thing to take away is it's really complicated. And this postage stamp right here, that's the structure, that's where I mostly hang out. But all these systems are touching and pulling and interconnected. And it's really good to see the full complexity of this. And then realize that if we're going to do design integration, we have to figure out how to kind of work in this messy world. So I think it calls for an element of design thinking and system thinking. And the best graphic I've ever seen of system thinking is also done by BNIM. This is for the Packard Foundation. And here you can see 6 incarnations of the same project. And the incarnations are based on a market rate building, all the way up through the LEED certified silver, gold, platinum, and all the way up to a living building. And so you can think if it's the same project, same program, over and over and over, and the only thing we're going to change is the environmental responsiveness. How sustainable is it? And a couple things to think. So within any building, there is a sort of a logic, there's an internal logic that is the design of that building. What that means is you can't simultaneously optimize all the parts. You have to optimize the whole, it all has to hang together. So the one thing I'd like to have you guys take away from this is notice that the form of the building is changing as you look at the different incarnations. It's a little hard to see, but this is actually the building section. The building section is changing. And then here, these red squares, those actually represent a year's worth of energy from a single family residence. Red means you're burning energy, green means you're producing energy. And so this is a really great way of marrying architectural design, early preliminary design, form, shape, program, and system thinking. So we've got energy, we've got grid reliance, we've got external pollution, we've got schedules, construction costs, first costs, life cycle costs, the whole deal. And this is it represents a very powerful kind of intellectual model where all of this can be held together to make decisions. So then now that we are going back to this idea of this messy world, we've got 2 images here. The first on the left is from Stuart Brand's How Buildings Learn. And in that, what's really sort of nice about that thinking is that you have it's sort of recognizing that the systems exist in the building, like the site, the structure, the skin, the mechanical system, the stuff. And recognizing that these systems actually have different lifespans, and they're kind of sliding by each other. So it's, you can say, like, I do a lot of work in seismic retrofits, and so I actually look at programs coming and going in different incarnations of the building and different lives of the building. So I kind of see this permanence of structure. But it starts suggesting managing the interface between systems. Like, how do we handle the boundaries and the tension of this? So that's one model where we think of separation and managing the boundaries. Now, another model could be systems are tightly integrated, and it's a puzzle piece, and they're all locked together. And I think buildings often, real projects, have some of both, but it's just a conceptual framework for thinking about, you know, are we managing boundaries, or are we tightly integrated and thoroughly coupled? And I'm not advocating one or the other, but I think as designers we need to understand what are these characteristics, and how does the world work when we're looking at projects through these various lenses. So I'm going to talk first about this is a little concept of design I did for an interview, and this is for a program, a junior college, and it's vocational training for, like, installing energy systems. Now, first off, this program did not exist 10 years ago, and we don't even know what it's going to look like 10 years hence. So the idea is that the program is variable. You can't optimize because it's really changeable. And so we said, well, let's take those layers and let's segregate them. Let's make a freestanding, robust structure that can allow a plug-and-play expression of doors, windows, walls, skin, and manage the separation, and then make a building that is kind of naked from the inside, completely exposed, that somebody could take a sawtooth for the studs, somebody could weld on the frame. And so in this, we purposely made this frame robust, meaning it's not optimized. There is actually a tension between optimization and robustness, and with robustness, there's flexibility. So here, this design called for flexibility. And so we're purposely not making, we're overbuilding, because we don't know what's coming. So that's an important decision. Now the next idea is one where it's a same college, different architect, Steinberg, different program. And this is a very special site. And what the architect is looking at doing here is making a building that sort of works with the landscape. There's a big sort of gesture about views, and there's a bluff over here, and you look over the ocean right over here. And so this building needed to kind of really manage how it sits in the site and be responsive and actually take the landform. And so this has green roof and all of these things on it. And so I'm coming up with a structural form that is highly integrated, like the puzzle pieces. So these are glulam ribs and purlins all tied together. And then if I zero in on this, and I started like imagining the structure, what we have are the glulam ribs that undulate, the purlins that are faceted, that accommodate the undulation. Even right in here, this is the structural decking. Now the structural decking has been opened and spaced, and there's an acoustic material on top of it. So it is both a piece of structure, an architectural ceiling that's been tuned for acoustic absorption and acoustic refraction. And so it's all together, and then we have the insulation and the living roof. And because we want to get this sort of basket expression for the structure below, we had to upturn the ribs because of the span. So this even affects the drainage solution of the building. So it's all tied together. Now you can do this early on because the clay hasn't set. And so this is the time to play with these ideas. You can't come in after it's all done and play with them because you start locking decisions in place. So now I'm going to go from conceptual framework to just trying to show ideas around integration and work process and trying to find this conversation between structural engineering and architecture within this broad context of design. So first is a project, it's the Chartwell School in California. The architect is EHDD. And one of the big ideas was this steel window frame system here. And the original vision was a welded framework. Now, this is a private school for dyslexic kids. They want LEED Platinum, really high sustainable aspirations, but they don't have a lot of money. And so they can't go ahead and just sort of, blow the budget. So we had to find some balance that worked for this design. And so what you're seeing here is a graphical conversation between me and the architect on how to make this frame. And so it's like, well, we can't afford welders up in the air welding, so we have to have a bolted solution. If we're going to bolt this thing together and we've got windows stuck in it, we need to deal with tolerance. So we need to sort of introduce a little shim space here so we can plumb and align this building because we can't go hack at it and we can't hide it with finishes because we need a certain level of precision to fit within the window. We even need to figure out a way to waterproof it, so we made this gap, this shim space smaller so you could go in and caulk around it. And it's going to be exposed, so let's actually study the types of connections, the types of bolts. This is just a conversation. That's all it is. It's not a design, but it's a way of talking about structure, architecture, waterproofing window systems, cost, and construction all at once in one graphical picture. And then on the inside, the expressed space needed a connection language, and again, another design conversation. So it's a simple shed roof with some exposed framing. We wanted some wood, we wanted some steel. We needed to sort of manage and work within this coming together of steel and wood. And so this, again, is how we're talking to each other. And yes, the animation works. And this is it. I'm going to relax for a second. So that's the exposed frame. And then we just have the exposed trusses and framework on the inside. So one of the ideas here for these kids, because they have learning disabilities, is that we were thinking that everything that you see needed to be transparent in its language. And so maybe a kid, and these are young kids, doesn't say understand architecture or structure or anything, but they need to feel that the space is right. And I'm talking about right in the sense that there's a sense of proportion, that the skinny members are in tension, and the members of impression that take bending or the right shape. Because what we were thinking about is that it either feels right or doesn't feel right, just like an instrument either sounds in tune or it doesn't sound in tune. You don't have to be a musician to tell whether an instrument's in tune. And we think there's something that may be going on with structure and space. So now I'm going to switch gears to another skeletal building. And this is with Methuen. They're out of Seattle, and BNIM out of Kansas City is the executive architect. And this is the sustainability treehouse for the Boy Scouts in West Virginia. And this is an exposed skeletal structure in the middle of a forest. And it's about getting in the canopy and experiencing the forest. And what's really nice, they call this, in Methuen's office, they call this the land of lost toys. These are all the designs that didn't quite make it. But what's really sweet about this is that these are explorations. This is a very fragile and delicate time for the architect. And this is the time where the engineer needs to come in and be gentle and help the creation and the nurturing of these designs. We don't need to look at this one and say, oh, if the wind blows this way, you fall over. And, we can point that out, but we need to do it in a really gentle way. Because this is a series of explorations. And eventually, the design started coalescing about this idea of a single super frame, these two pods, the occupiable space between and the occupiable space above. And we started thinking, it's like, okay, we need to build it. What is it? How big is it? How's it working? What is the structural language, the connection language here? And literally, I'm taking the model and working the model and working with the glue gun and moving and cutting pieces together and creating this thing with the architect. And then going into Rhino and developing a language. Again, this is about finding, there's lots of ways to make a column and connect a column, but how do we do it? You know, what is the expression of that? And then thinking about this explorative view, how do we make a base? Then how do we put a pod on it? How do we make the second level another pod in the upper part? There's the inception and the creation, and it all has to be held at sort of at the same time. And then drilling in a little deeper, it's like, how does the base touch the ground? You know, what is the shape of this gusset? What is the form? What is the language for a bolted connection that still has to be a moment frame, and the mirroring of wide flanges and tubes? So this is what we're finding and discovering, and this is the final shot of the project all coming together. And you can see it's all out of core 10, and so you can think of this as both the separation elements, where you have steel separated from the occupiable spaces, but even in the pods right here, these are tightly integrated. So both of those models of the nested puzzle pieces and the sliding layers occur in this one building. So here you see the base coming down right here, and the original model. And we're working in models because all of the sort of look, feel, cost, constructability, all of this matters here because it's all exposed. And then here's the moment joint, and you can see there's the row of bolts, and that's where it all comes together. Here's the interstitial space between the pods where the kids are hanging out. Another one. And the final shot with a sort of a glow. So for the next project, this is a renovation. And in sort of modeling, you know, sort of taking really nice ideas from the architectural world, I love the idea that designers and creative people will develop precedents, good ideas from other people, and pin them up on the board and say, isn't this wonderful? Isn't this wonderful? Isn't this wonderful? So the reason I brought this project out, is because we actually have a structural precedent that I found for this. Let me tell you what this building is. The architect is SOM. It was a 1960s bolted moment frame building in downtown San Francisco. It means really intense earthquake country. It had a precast concrete frame, skin on it that was taken off, and it was reclad. 2 stories were added to it. Horizontal additions were done to it. So it's a big sort of re-inception of this thing. And then the structural precedent is the Japanese pagoda. And 1,000 years ago, Japanese temple builders figured out that they could build a 5-story wood structure with just wood traditional joinery. And they could stack it in earthquake country. And by introducing a single cedar pole, which is called the shimbashira, this piece, it's a pole that actually sits in a stone well. So like if you took this pole and put it on the base, it would fall over. It has no strength, but it's a circuit. And so when the ground shakes and the bottom story tries to distort, the pole, the shimbashira, engages it and makes the lower portion talk to the next level and talk to the next level and talk to the next level. And so when you see models of this, you see a temple will sort of dance like a snake as the ground's moving, because there's this circuit going on. Now you can't find this in a statics book. It doesn't satisfy statics. It only satisfies dynamics. Now, I have no idea how temple builders 1,000 years ago figured this out. But right now, we use really fancy nonlinear analysis to show that this works. So in our building, we have a reinforced concrete chimney on a pin base. And this is the space for the stairs and the elevator and the mechanical system. So it's an integration of structure, mechanical, and circulation, all on the central spine. And come on. Here it is. There we go. So this is the original 1960s frame. There's a removal of the old penthouse, opening up of the floor. This element is 30 feet by 30 feet. It's about 18 inches thick for the concrete, so it's heavy. So we've got micropiles at the base. There's its foundation. And that is the pin. This is a base isolated pin. This is what this element sits on. Think of it as a pivot point. That is the foundation that sits on that pin. And then here you see the base or the spine connected to the floor with steel dampers called buckling restraint braces. They accommodate the deflection compatibility and bring the flow of forces in and out. And then you have the addition and pop-outs and all the rest, and then you skin and cladding. And finally, here we go. That's just a close-up of what that base looks like. So now I'm going to switch scales, and I'm going to talk about the little team project. This is a prayer wheel pavilion. So this is for a Buddhist retreat center in Northern California, and I designed this with the Lama, who's an artist, but not an architect. And what a prayer wheel is, if any of you don't know, these are like 10-foot tall drums, and they're full of microfiche. And on the microfiche are Tibetan prayers. So this is a goodness machine. And what happens is the motors spin these wheels, and wonderful things emanate from this building. So it's a very important pavilion. And what was, these are the three-dimensional models of it. So this was all designed in 3 dimensions because we're working with big, heavy timbers, and it's very hard to draw big, heavy timbers that are coming in at weird little angles. And the thing, there's one thing I want you to leave you with, is the Lama hired a master timber framer to teach me the art of timber frame. And so, and it's the place where craft is in design. That's the message I want to leave you guys with. So the timber framer knows all of these things about engineering and architecture through this language of timber frame, and I was the student. It's really appropriate for a Buddhist center that you have to let your ego go. And I was the only design professional, and I'm being taught, shown how to do stuff by the artist and shown how to do things by the craftsman. But it was really, really, really cool to learn how to make these joints, and then figure out a structural form that made sense and it was beautiful and exposed. And this is the pavilion in snow, and then finally lit up at night. So now I'm going to switch scales again. Go back up. This is the San Francisco Public Utility Building. And so this is a big building, and part of the utility's essential operations are housed in the building. So this has a really high performance mandate. And since this building in earthquake country has to be able to take the biggest, nastiest earthquake that we know how to deliver, like the 1906 happening again, go through that earthquake, spring back, and not have any damage. So you can keep running the utility. That's the design mandate. About 12 years ago, the design was originally base isolated by a very famous engineering firm that Marcy used to work with. And they were able to hit the performance mandate. And in base isolation is where you have this slipping plane, so the loads can't get into the building. They couldn't afford it. So then about 7 years ago, they came up with another technology, or used another system, which was a steel-bolted moment frame with hydraulic shock absorbers between it. So when it would displace, the shock absorbers would convert motion to heat. And that project went forward. And after a really brutal value engineering cycle, they found they were still $10 million short. So there's a $130 million budget, and so they've just gone through this nasty value engineering cycle. Now the builder, Webcore, knew some of the work I've done in reinforced concrete, and what I came up with was the idea, and it's sort of a borrowing from the bridge world, is you take concrete walls and you put vertical post-tensioning down the middle of it. And so when the earthquake happens, I'll demonstrate, the wall flexes, but think of this as a giant rubber band down the middle, and it springs it back. And so if you think of like concrete as liquid stone that you put in the mold that becomes a rock, then you add reinforcement, so that's a ductile rock. Now you add a spring in the middle, and you have a ductile springy rock. That's what we made. Here's the structural animation of that. So this is the ductile spring rock. So it's a new technology. That means there's invention, there's risk, and a whole bunch of stuff like that. But remember, the whole point of this, and the reason I'm bringing this up for you folks, is that we're trying to save $10 million. And this is not about the structure. And so we can save a little bit in the structure. Let me point out for a second. There are these ducts in here where the post-tensioning will come. But really what we're trying to do is figure out where do we get that money in all over the place. So here we've got a coupling beam. This is how you get in and out of these vertical cores. This is where the circulation goes. So this is one innovation. It's a coupling beam that's like a precast element or a steel element that flexes, dissipates energy, but it's also formwork. So we're thinking about construction process and technique with the builder. Here you see the post-tensioning ducts going up there. Now we've got the two towers. And what's going to come next are the vertical post-tensioning cables from the top. So at this point, we're working with bridge consultants to show, to figure out the best way to stress these things, and we pull on them. And then finally, the building is, we've got the steel framing on top, and it's clad. So remember, the story is about the $10 million. How do we get the $10 million? So the first thing we're going to look at is the skin. The skin costs $30 million. The structure doesn't cost nearly $30 million. So if you think about the economic hierarchy of the project, the skin matters more than the structure. So one way you do this is we went to the folks who make the skin and we said, how far can your skin move before it gets damaged? Because we also have this high performance mandate. So normally, in a normal process, you design a building per code, then you may do a fancy analysis if you get paid more, you see how far it moves, then you look at the skin and you see that you broke the skin, and then you go to the skin folks and you say, could you open up all your gaskets and spend more money to make the skin more flexible? What we did is we said, we can only afford the skin we can afford. Why don't we find out how far it can move, and then we'll figure out how strong to make the structure to not break the skin. So we reverse engineered the process following the money. The next thing we did is we spent a lot of time getting the floors thinner, because by getting the floors thinner, especially in the steel counterpart, we're able to save 12 inches at every story. By doing that, the amount of skin that we need goes down. But the owner was able, now we're thinking about the business, they were able within the zoning envelope to add another story. And so we didn't make any more money by making the skin cheaper, we made more building by making the structure thinner. And so in terms of the value engineering, we didn't just cut cost, we went and we added benefit, which was the extra story. We changed the pro forma. We also went after all the finishes And so it was about getting rid of the architectural finishes. There was even an element in the spec about the color of the concrete tied to the lighting design, because we were looking at making the lighting system work better and saving money on the electricity. And there was some money saved on improving the thermal mass of the building. So the point is, we found the $10 million by looking at all the other interconnected systems, going back to the puzzle pieces. So when we went from steel to concrete, we were looking at how we were looking at the connective tissue of the entire building and figuring out how we could save every place we could. So here's the punchline. At the end of the day, we met the immediate occupancy requirements. We got rid of the 12 inches per floor, but then we put it back as a new story. We improved the thermal mass, which changed the energy models. We also did collaboration with the concrete supplier and came up with low cement concrete. So we did a design shred on concrete, cut carbon footprint by 50%, and got the $10 million. And so the point is that you know, to me this is a really good story about system integration and design collaboration. Now I'm going to switch scales again. Last project, really, really small. This is a single-family residence for Lou Harrison. Lou was an avant-garde composer of the highest order, and this was his retirement home out in the desert of Joshua Tree. And this is a building where you can think of it as all one thing. So the architecture, the form, the skin, the insulation, the structure is all one object, which is the load-bearing straw bale. So this is the structural diagram of the load-bearing straw bale. The architect is Skillful Means, their design build group, and they came to me because they wanted to figure out how to make this vaulted roof in a great room. And they originally only budgeted a vaulted roof made out of stucco, wire mesh, and straw. And they had another design that had a backup internal structure, and they couldn't afford to build that. So the first thing I did was said, let's go back to the fundamentals of behavior. How do you make a straw bale arch and vault? So we came up with a reinforced theory for flexure and a theory for shear. And this is a direct adaptation of strut and tie modeling from reinforced concrete. Except instead of concrete, you've got straw, and instead of rebar, you have wire mesh. So it was an idea. And then from there, came up with a full-scale, a test where we made a full-scale 4-foot slice of the wall. And I came up with this loading apparatus where there's a hydraulic jack in here, and you pull from the saddle, and it goes around the pulley, and you pull out from the saddle. And that emulates seismic loads during an earthquake. So this is the straw bale building community coming out to witness the test. And after the test was over, this was the vault. So it looks a little shaggy, but what we did is there's the loading saddle where we pulled in, the load goes through a pulley, goes around another pulley, and pulls out. And that's the lateral loads. We got volunteers to help with the testing. And we took this building and we subjected it to about 130% of its weight sideways. So they'd be like taking it, turning it on its side and shaking a little bit. And then after that was done, we had a whole bunch of people pile up on the roof to do the gravity test. So back to that point about not needing precision or accuracy to make a decision, all I needed was confidence that I could build this. And so, it's kind of hokey and it's country granola, but I think it's good sound engineering. So just a couple of construction shots. This is at the spring point where the vault hits the walls. This is me and my wife at the bale raising. And the final shot. So now this is my last slide. And it's kind of a boring slide. But this is, in some ways, the most exciting slide for me. This is a project that's going on in our office right now with BNIM. It's also for the Boy Scouts. And what we're doing is we're collaborating across, a couple thousand miles, using SketchUp models. That's how we talk to each other. And there is a direct sort of, this is the architectural master model. And it's just planes and form. It's very light. And this is what we're developing through the conversation and WebEx calls. So we understand that there's this really important view corridor here. We understand the nature of the site. This is on a bluff. We understand that this is a light piece that hangs over the hillside, and then there's a heavy zone that is locked into the hill. And then there are these classrooms, and then there's a more massive conference room. So we understand the ideas and why things are going on. So we're not, we're sharing it. And then what we're doing is we're doing just enough analysis, like literally precising one joist and one little moment frame and some decking. Just enough so we know kind of how big stuff is, and then we're modeling it. Because what's really important is what does this place look and feel like? Now, one of the big values of the Boy Scouts is thrift. And it's really important that I get the direct transmission from the owner of what they value. And so we need it, and what that says to me, it's like thrift. Okay, that means this has to be straightforward. That means it has to be clear. It has to be kind of elegant. They also really like design. But it can't be wild. It can't be wasteful. And so we have a program that has this intersection right in here. And when you do conceptual design, usually what you do, normally you work on like a simple slice through here, and a simple slice through there, and then maybe a simple slice through these parts. And what you never do is look at where they all come together. And this is where all the money and time will be spent on this project. And this is where it's either going to be really nice and tight and kind of cohere, or it's going to be a big sloppy mess. Because there are no finishes and everything's exposed. So we're holding to the owner's value, and we're saying, we need to get in here. So when we're framing and building this model, we literally move the buildings. And I think it's the coolest thing in the world that a structural engineer would move a building. Because in the hierarchy, and who rules the roost, owner, architect, the help doesn't move the building. But we're getting to move the building. Because we're needing to really dial in what's happening right at that point. And that's where this thing comes together. And it's really cool and really fun. And I think we're going to have a nice, handsome building. And the only point of this is for fundraising. So you need to be able to see it and get cost. And so the owners, so the builders need to get a sense of complexity and how tough are these spots. And so it's a really nice experience for me and experiment in how to do collaborative design. So we're doing this model-based front end in about 4 projects right now simultaneously. What we're finding is there is no schematic deliverable, because we always throw that away anyway, and we're finding that we're able to do it easier and for less money than a traditional design process. So we're having a lot of fun, and it makes business sense. And that's it. Ready for any questions you folks might have?
Jason, we have time for some questions. Who has some questions?
Yes.
In this process, I have found in various things that I've done that the devil is in the details. And sometimes you can be pretty far along and actually get surprised.
Yes.
And I'm just wondering, with your sort of sketchy analysis at the beginning, just kind of get confidence, does that leave you with more room to surprise?
I don't think so, because if I go backwards, I think it's a great question. So with this model is a whole pile of trace paper where we're exploring the details. And one of the things we're really exploring is thermal bridging and how materials conduct and how we're managing the thermal envelope. And we're trying to have this model reveal the really knotty parts of the building. And we're trying to solve that problem while the building is still really plastic. So what we're doing is by modeling this thing in 3D and looking where it comes together, we're trying to see where we're going to have trouble. So we're looking for the place that you're worried about in the process. And the hope is that if we can find it now, we have lots of options to manage it, deal with it, that we wouldn't have later. But great question, thank you. Please.
Just follow up on what you said about thermal bridging. The charcoal school with that steel detailing the facade. How could that work with a leaf pattern?
Yeah, well, it's interesting. It's a great question. I was hoping nobody was going to ask it. We would never do that for West Virginia or the Midwest, but this is in California. And so at the end of the day, we have more PV panels than we might otherwise have. And that's just the simple truth. So it's bridging all over the place. And that's, you could say from a mechanical standpoint, that is not efficient. You could also say from an architectural standpoint, it's really important that it look a certain way. And there is a design tension or a conversation around that. And you're absolutely right. Yeah, it's a big, like, don't put an imaging thing on that wall. But it is a gymnasium space. The good news is that the kids are the heat generation source there. And no, seriously, that's what happens in gyms. And so it can be a little cooler and a little less efficient. You couldn't get away with it here, but in California we were a little sloppy. Thank you, Sam.
Yes.
How do you get your structural or your seismic ideas approved when there are not really too many local or modern precedents to them? I'm thinking particularly the Shimbasura because I don't know of too many other examples like that
Right.
exist in the last 200 years.
Yeah. So usually we have a peer review process. And so we go to the building department and we say, we want to propose an idea. And they set up a formal review with an expert. So in this case, it was a Stanford professor, Greg Dearline, who was our reviewer. For the straw bale vault, we also had a peer reviewer that was with Ginny Elsner. And for the post-tension cables structure of the PUC building, we had a team that included a Stanford professor and another practicing engineer. So that's how we do it. Sometimes when we want to design resilience, we design a version that meets code, and then we provide the self-centering as an added feature. But part of the tension is finding, making the economics work for these designs and dealing and managing the risk of the performance. So it's a tightrope to walk. Great question.
So I guess I'll have the last question. So you've embarked on this new firm and this new approach to engineering. How do you find architects are receiving it?
It's really great. It's really great. What we're finding is that people are excited to work together. Our business model is that the building would be a better building, like better, not just better structure, but a better whole building, and that you do this as a team in collaboration. What we find is because architects are taught to collaborate and synthesize lots of ideas from lots and lots of systems, Let's see if we can get you back or not. That they're really receptive. Now, I have had clients who, you know, you're to be seen but not heard. And I'm at the age where life's too short to work for those folks. And so what I want to do is say, this is a model of work, and whether the firm grows to be 15 people, 20, 30, 40, we'll let the market determine that. What I'm looking for is my sort of design kindred spirits all over the country. And that's why this experiment with working with the Kansas City architect in this very intimate way is really exciting to me, because I think this is, like, it's just more fun to work this way than otherwise, and I think it's more fun for the other folks across the table. So far, so good.